Ladies and gentlemen, welcome to the third Aboagora symposium. Nice to see you all here. And we welcome the sun also. You all brought the sun. Gives us a little reflection also, which might disturb us, but goes away soon. So Aboagora is a big joint Turku effort in order to try to embrace science and arts. And this year we concentrate on the complex subject of the relationship between the human and the machine. So welcome you all from all the corners of Europe, from all the corners of Finland. My name is Topi Lehtipuu. I'm one of the members of the organizing committee. Here I have next to me Asko Nivala, who will be, who's mostly in charge of all the practical matters. So if you will have any questions concerning those things, please address Asko. Today, we start with a very special subject. Our next speaker, he's a professor of cybernetics of the Reading University from UK. He's not fiction. He's not the Terminator. He's not the Robocop. But he's the first cyborg. Please welcome Professor Kevin Warwick.
Sorry if you're expecting to see Arnold Schwarzenegger come out of there. You got me instead. And I have to admit, before I start, when I was a young boy, I tried to learn to play the trombone and failed dismally. So because I didn't succeed at doing that, I ended up doing this instead. The Terminator, which was that's where the music was from, was looking at the possibility of intelligent machines or cyborgs of a type, part human, part machine, taking over from humans. And I guess what I'm looking at are the realistic possibilities of that. But looking at how, in different ways, humans and technology merge together, and how, with the title, different pieces of technology are becoming more human-like as well, particularly computers. So towards the end, I'm going to be looking at what's called the Turing test. This is about computers pretending to be machines in communication. And it will be in English, so hopefully your English is okay, that you can follow actual transcripts. What you'll see are pieces of communication between human interrogators, and you won't know whether it's a machine or a human. You're going to have to try and work out yourself from, these are actual transcripts from last year, so you've got some homework to do. When this comes on, you're going to have to work. Before then, though, I'm going to talk about actual experiments. So this isn't particularly artistic in any way. This is the science that I'm involved with and the experimentation that I'm involved with. And I'm going to start with what is now called biohacking. It's often with science, you do things in the laboratory and you have a bit of fun and you get scientific papers out, and then a few years later it gets a sexy name attached to it, and that's what happens here. Now biohacking is quite a sexy name. At the time it wasn't a sexy subject at all. He wasn't particularly sexy. This is me. Hopefully the sun is blinding out the bits of me. This is way back in the last millennium, I have to say, 1998. And various scientists and the sort of science gurus that you get were saying that in the future we're not going to need passports, we're not going to need credit cards, we're not going to need keys for cars. What we will have is a little implant under the skin that identifies us, a piece of technology in our body that identifies us to the system around us. But nobody had actually, no human had actually tried it until I did. So this is me, or was me anyway, years ago. And this was my doctor, so this is just my local doctor. And what he was, you can see he's implanting in my left arm, not this thing. We still have this old currency in England. This is what was implanted. And so it gives you some idea of the size. It was 2.5 centimeters long, quite a big thing. This is called a radio frequency identification device, RFID. Now it's better known in that way. It works in the same way, really, as a smart card. This will pick up over about 2 meter range, 2 meter distance. Certainly 1 meter is very, very good. So it's a bigger pickup than you would typically get with a card right next to the reader. This was implanted in my left arm, and what I was able to do was to indicate my presence to the computer in my building at Reading. So, and we'd got the computer linked up to different points in the building. So as I walked around, the computer knew where I was at different points, and we got it to do things for me. So when I walked down the corridor, the lights came on automatically. Yeah, it was pretty cool, I have to say. I mean, remember, this is 1998, and you've got the building doing things for you. And going to my laboratory, and the door opened automatically, coming into the front of the building, and the computer says, "Hello, Professor Warwick." It was absolutely fantastic. Partly, at the time, we were trying to show what you could do with an intelligent building. If the building knows who the person is and where the person is, so it can do things for the person. So we were trying to show that. But partly because it was implanted, it was part of my body, and hence the computer was doing something because of what was in my body. And I learned very quickly in talking to other people when I had this implanted, that people that have technology implanted, this is different. Some of you are wearing glasses. You can put glasses, you can pick them, put them down and things like that. But if you have it implanted, very quickly you mentally think of it as part of your body. So that includes people with artificial hips and cochlear implants and heart pacemakers. Lots of people have technology inside them now, but they don't think of themselves and the cochlear implant. They just think of themselves. It's part of them. It's part of their body. And this was the same for me. It was part of my body. And hence, it wasn't because of this technology doors were opening and lights coming on. It was because it was me going down there, which is important. Now, some people criticized me at the time. Why do you want to do that? No one's ever going to want to use anything like this. This technology in a smaller version is now used in quite a few places. Does anybody have a cat or a dog who has a chip implanted? Thank you very much. There's quite a few. Yes, don't be shy. This is always fine. I think for those of you that do, you can be happy that this technology was fully tested on a human before your animal received it. But one of the biggest uses now is in the United States. Back in 2004, this was first given the okay for use in people that have diabetes and epilepsy. It's a bit like having your medical record in your body, but the reason for it is if you're rushed into hospital, the medical authorities can just scan you effectively and know what medication to give you from what's on the implant, and the information can be updated and so on. So it can be life-saving to have this in your body. And because if it's a card outside, you can lose it, whereas if this is in your body, it can be very, very useful. The issues with that now, under the Obama healthcare plan, this is now regulated, and there starts to be a bit of a feedback loop that to receive support and appropriate in different ways, you have an implant of this type. So if you have an implant, it must be registered, but to be registered, you must have an implant, if you see what I mean. So it's one of those ways you tend to think a few years ago, well, no one would force people to have pieces of technology, but there are ways. If you want this particular service, then you would need to have this piece of technology. Different ways of doing it. Anyway, there's the first experiment. I'm now going to bring you right up to date with what some of my students are doing. So, and this is the sort of thing, if you fancy having an implant yourself, have a bit of technology, this is the sort of starter kit that you can do. And I have 3 students now that have magnets implanted. And this is to show you what happens. This is Jawesh, and what he's having, you see the guy here is making an incision on the finger. Sorry if you had a big breakfast this morning. It gets worse, I promise you. So it's a small incision, and then a magnet is put into the finger. Now, we have to get ethical approval from the university to do, and you know what universities are like, it's sort of boring people in the committees and things like that. But we have to get ethical approval. And here's a bit of a problem, because you see the guy that is actually doing this, And he's actually got tattoos there. I'm not sure whether you can see because of the sun, but he's got tattoos on his arm. So he's not a doctor or any, well, I say that, he's not a doctor. He's a tattoo artist. That's his job. He makes tattoos on people. But he goes by the name of Dr. Evil. That's what he calls himself. The problem is, on the ethical approval form at the university, there is a line that says who is carrying out the medical procedure. There we go, Dr. Evil. So it creates issues for us, to say the least. But nevertheless, I have 3 students that have this. This is Jawesh. You can see an X-ray of you see the little magnets we're talking of here. So these are implanted in the fingers, and they stay there. You know, they're permanent magnets, permanent implants. Now, to show you what we're doing, we're looking at it scientifically. There are some, dare I say, artists that are trying this for other purposes. We're looking at it scientifically. And what we do, on the baseball cap, these are ultrasonic sensors. So this is like a bat sense. It sends out a high frequency signal which then bounces off an object if there's an object there, and hence the signal that comes back, you get a direct, pretty accurate indication of how far objects are away. It's the same principle as submarines use for bing, 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 to get an idea of distance to objects. So that's the ultrasonic sensor. The output from the ultrasonic sensor is fed down to a little coil of wire which is around the finger. So Jawesh there has got a little coil of wire around the finger. In his finger is the magnet. So what happens, as an object comes closer or Jawesh moves towards an object, the current in the coil increases and the magnet vibrates more. And Jawesh can feel the magnet vibrating. So essentially, the closer the object is, the more the magnet vibrates. And the further away an object, so the magnet vibrates less. So if there's nothing there, the magnet doesn't vibrate at all, so it can move around. Now, clearly you can see, potentially for somebody who is blind, this could be useful. They instead of having a stick, they can just walk around, and they would feel when there's an object nearby to them. Which is what we're looking at. It's sensory substitution. It's taking a very strong touch sense, but using it for distance to objects, which humans are not that good. We may think we're brilliant with our stereo vision. It's really not that accurate. And here you can get a very high accurate indication of how far objects are away from you. Now, I also have Ian Harrison, who's doing a PhD with me. He's looking at a range of different sensory input. Instead of ultrasonics, he's looked at infrared. Now, infrared is like a heat signal. So what he can do is get an indication of how hot objects are a distance away. If you see, which again, we don't know. We don't know how hot. We can touch it, but if it's a distance, we don't know whether an object's hot or not. With this, you can actually feel how hot the object is. So he can literally, with his sensor, go, you are hotter than you, and in a temperature sense. Maybe in other ways as well, but in a temperature sense. So he can get an indication, and it depends on the sensor as to how far the signal comes back from. But so it's giving a human a sense of heat from a distance. But of course you can do all sorts of things with this. We're trying to communicate with it in a different way. Now here, it's not really helping anybody with a disability. It's giving everybody potentially extra abilities. And one thing to note from this is that humans, as we are very limited in what we do, physically and mentally. One of those ways is in terms of how we sense the world. Our 5 senses just give us a very limited frequency spectrum on what's going on around us. And this is looking at different ways of increasing the ways in which we can sense the world. Ultrasonics, infrared, X-rays, ultraviolet. So there's whole ways that we can increase our sensory input. We'll see more of that later on. Importantly, the brain is quite good. Our brains are quite useful, and if we put new signals into them, they can adapt. They're not stupid. What does it? Well, our brains can deal with new stuff. It's not difficult. So let's push them a little bit.
That's technology, not science.
Well, we can look at it as science if we take measurements and see the accuracy and the response of the brain. Pardon?
RFID also does that.
Yeah, sure. But that science is investigation and taking measurements and reporting on the findings, and that's what we can do here. Sorry?
Definition of science.
Okay, I will give a bad definition of the science, and as long as everybody can put up with my bad definition of science for this presentation, then if you'll let me talk, and at the end, if you want to discuss what my definition of science is, I don't know, just to be accurate, whether I actually said what I'm talking about is specifically science. Okay, if I said it, thank you for telling me what I said. If I said, I hope with the audience you don't mind if I press on with the presentation. If it's okay, sir, we will discuss whether it's science or technology or what it is towards the end, if that's okay. I'm going to look at another, what I would like to think of as scientific experiment. This was done by, first of all, by a chap called Paul Bakirita. I think he thought of himself as a medical scientist, but I'm not sure now. This is looking at different ways of communicating with the brain. And so this is another student, so it's the sort of thing that the students can try and so on. Now what he has built there is a little device that you put on your tongue with a series of electrodes on it, which essentially send a very small electric current into the tongue, little pulses. And when you put it on your tongue, so you can send different patterns of signals into the tongue. So what this is for communicating with the brain in a different way, in a different route. And reasons for this, scientific or not, are that various technological companies are having problems with the information that is available, for example, in cars, one example, getting that into the human brain as quickly as possible. And the visual side of things is being really filled up, is overflowing. So they're looking to get pieces of information about you need to brake, there's somebody overtaking you, whatever it happens to be, quickly into the brain in different ways. So that's one reason for looking at this particular piece of technology. So what you're able to do with this is to put different pieces of current into the tongue via this bunch of electrodes and to send patterns into the tongue to see if the brain can recognize them. And this is a very rapid route into the brain. It's a lot faster, in fact, that by taking measurements to see how quickly the brain responds. It's a lot faster than putting different visual cues in. So it's a very, very rapid way of communicating with the brain. And you, even if you haven't used this before, very quickly you can pick up and recognize patterns, little triangles and so on. But what it is useful for is sending directions. So you can, if you've got a particular point of reference, it can send you a signal to direct you, or to send you go forwards, go backwards, go left, go right. So it can give you where is a good direction to go. And it's very easy to discriminate those particular things. So what this is a new way of communicating with the brain. I mean, what we hadn't thought of with starting looking at this is that with babies tend to put a lot of things into their mouths. Those of you that had children, to start with, sort of almost learning to recognize objects and so on by putting them into them. Everything goes into their mouth. which trying to figure out what is the reason, why do they do that? There's various speculation, but the science behind it is of course quite limited. But here, looking at it, what I would like to feel of is a scientific way, by taking measurements and seeing how quickly it responds. We're perhaps getting a handle on it. Maybe we'll find some reasoning. And as adults, we don't tend to do that. We eat and we drink and so on and so forth, but we don't tend to use the tongue to send signals into the brain to understand what's going on. Well, maybe we could do. Maybe we could use it. Maybe in later life we have sensors there that could be useful. Now for something a little bit different. Those of you that have thought of robots, you tend to think of as maybe some programmed little car that's moving around, and or a human controlled device that is used for blowing up bombs. Well, now we can look at it other ways. We will see in a second robots that can have their own brains that we can grow with biological brain cells. First of all, though, I want to give you an introduction to some of the robots I get to play with. The sun's disappearing. So I'm going to show you a clip from a BBC programme called Inventions That Changed the World. There's two lots of robots. The first robot is Morgui. Morgui has 5 different senses, and we're looking at integrating the data from the senses. We'll then see subsequently some little robots, little wheeled robots, and it's more those that are relevant to the presentation now.
One of the AI community's leading lights is Professor Kevin Warwick.
Well, this is a robot head.
Dissatisfied with vacuum cleaners and robot dogs, Kevin's gone one stage further. His cyborg comes complete with
Radar in its nose and an infrared top lip.
Is it intelligent?
Well, in a very limited way, I guess it is. It's sort of a basic instinct. What do I do with this information that I'm getting? How do I move? How do I operate if this signal is different?
So what's it doing now?
Well, if you clap your hands...
Oi, over here. Oh, it did it.
It's making basic decisions. All we've got it doing here is programmed to make basic decisions based on that sensory information that's coming in.
Getting the information in is nothing. That's like picking up a book. That's not an intelligent thing to do. Reading the book and knowing what the words mean, that's surely the intelligence.
Many machines can read books nowadays, but it means something different electronically to the machine as it would mean to a human.
Though the cyborg head does a reasonable job of sensing, it can't really interact with or explore its surroundings. It's fastened to its robot arm. And according to Kevin, it's only as intelligent as a dishwasher. If that's a dishwasher...
Yes.
Where are these in terms of... Are they dolphins, chimps?
I think you'd have to say it's about the 50 to 100 brain cell area. So realistically, you're talking slugs and snails.
But a slug and a snail, they know to eat. They know. These things don't...
They have some innate abilities.
There's no self-preservation with that.
Well, we do have. The power supply, they don't have their own batteries. They each have power they're picking up from the floor here. That's where they're getting their energy. That's where they're getting their food
But
from.
if you turned off this section of the floor...
If we turn off this section,
was here,
they have a basic instinct to go and look for some power somewhere else.
They will
keep going to do that until they find some.
So if I put him down...
It should go off looking.
So he'll have to go and look for power. And I got to tell him to do that.
No, it's an innate response for that robot. It's a basic thing of its life. Yeah.
No, his lights have come back on.
Lights are coming on.
So he's found power.
It's happy now that it's getting power. Away to go.
But these, then, are as intelligent as slugs.
It's different. But in terms of numbers of brain cells and that sort of thing, yeah, we have slugs. Probably you could say we're up to bees and wasps, the sort of tens of thousands of brain cells, is about as good as you can get. Yeah.
Bees and wasps.
Yeah.
Right.
Now, I have to admit that the original quote from that, if you look on Wikipedia, I know you never look on Wikipedia, but if you did look on Wikipedia, the original quote is that our robots have 50 to 100 brain cells, which makes them about as intelligent as a slug or a snail or a Manchester United supporter. But the BBC didn't like that bit. Now, those robots there have microprocessors for brains, so that's what's controlling them. We can look at how they learn, we can look at how they communicate with each other and teach each other and all sorts of things like that. But what we've done is replace the computers as the controlling element in the brain and with biological brains. So just to show diagrammatically, we'll see some robots in action in a second. This is the technological body of the robot. So the little thing on wheels that we saw with ultrasonic sensors, that's the same. So we're not changing that. That's the technological body. On the brain, though, this is an MEA. We'll see what that is in a second. Multi-electrode array. Essentially, it's a little dish with electrodes in the bottom of it. And in there, we put brain cells. Now, typically, the brain cells are taken from rat embryos, and we separate them with enzymes, and then it has to be kept, because this is living tissue, it has to be kept in an incubator at 37 degrees centigrade, and after about 10 days, we link it up to the robot body. So we have the technological body and a biological brain. The number of brain cells are anything from 100,000 to 150,000 is the sort of number. We don't get counting all this one, we've got 142,000. But it's that sort of ballpark. And they're very randomly distributed. I mean, it's amazing looking under the microscope. These are brain cells which are freshly put down, which have been separated. Within a few minutes, say 20 minutes, they start to push out what look like tentacles. And these tentacles wind around, and so this is what brain cells do inherently. They try and link up and communicate. They send signals to each other and then form pathways through the brain. So it's no surprise when people get addicted to Facebook and social. It's not your problem, it's your brain cells. That's what they like doing, is communicating and linking up and things like that. And we can see it happening under the microscope. And we play that to our advantage. So this is the multi-electrode array. These little rings here, referred to as Potter rings, are to try and stop it's a culture, but I'm calling it a brain here, as you'll see, because in the robot body, that's essentially the decisions are being taken by the culture. And it develops in here. The rings are to stop it dehydrating as best as we can. There are electrodes on the bottom in the center of the dish, and then we can send signals into the brain and pick up signals from the brain and link that up to the robot body. So essentially, when the sensors pick up signals, zing, 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 they stimulate the brain. Zing, 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 through the neural pathways, the output from the brain will then cause the robot to change directions. So the signal, the decisions to change direction are just being given by the biological culture, the brain, not by no computer is coming in saying what I think the brain wants to do is this. That's not happening. It's a decision directly from the brain. Now, to give you some idea, it is technologically limited at the present time. So we can have perhaps about 100 electrodes at the moment. Now, I was saying we've got 150,000 brain cells, and we've got 100 electrodes which we're using both to send signals and pick up signals. And you get some idea. The electrodes at the moment, this is what technology has, are 30 micrometers in diameter. Now, neurons, by all means, if you want to get scientific backup for this, scoop some of your brain cells out tonight, and you will see they are typically 2 micrometers to 20 micrometers diameter. That's the sort of nerve fibers are the same. 2 micrometers to 20 micrometers is the size of one of your brain cells. And hence, these electrodes are relatively big at the moment in comparison. We could do with them being a lot more of them and a lot smaller for what we're doing. But technology will improve. I've now got, this is a robot with, so we're giving it a signal to drive forwards, but what it's supposed to do is detect the wall and turn right. That's all we wanted to do. But the decision to turn right, there. So that was the brain, the culture making that decision. Then it sort of turns around. It wasn't supposed to turn around and crashes into the wall. This is only a 10-day old. The culture is 10 days old at this time. So it's early days for it. And we'll see some of the time it will get it right. I think if we look now, it will come and detect the wall and turn right. That's what we want it to do. And that's not what we wanted to do. But that's fine. This is only a 10-day-old robot, as it were. So it's got time to develop and so on. Now, one of the things we are looking at with this is how the culture learns over time. So typically, the brain, the culture, will be in the robot body for about 1 hour every day, doing this particular task, so it's a bit boring when you think how many brain cells are involved. And we can look under the microscope and see how the neural pathways change over time, which is, for us, it's tremendously exciting. And it's difficult to say this neural pathway strengthening means this, but we can see where neural pathways are strengthening and see how the performance of the robot changes. So we can link up brain structure and actual external operation, a little bit speculatively, but it gives us some idea. But we're looking at all sorts of things. We can enhance the growth, so we can speed up how quickly it learns. We can cut down, we can kill parts of the brain, so to see what happens if part of the brain dies off, as would happen with somebody with a stroke. Can the culture learn in other ways? So there's all sorts of things. What we're trying to figure out is how memory of being in a particular position, how they actually manifest themselves in the brain. Obvious links with things like Alzheimer's disease. So now what I'm going to skip ahead, we've now gone ahead, just like in the Terminator, we've gone ahead 2 months in time. It's the same robot, it's the same brain, and we'll see how it is now. So all it's been doing is what we've just seen. And remember, what it's supposed to do is to detect the wall and turn right, in this simple task. And we see it do that, and it turns right. And hopefully you can see very quickly how the robot has improved its performance. Now, in true MIT fashion, I've picked a good example here showing you how one is working. They don't all turn out this well, but it's the same with children, I assure you. It's no different. The important thing is that it can turn out this well, and does. This particular one is, because this robot has had a university education. This has learnt, hadn't had to pay fees, despite that being part of the process. The other things to say, I started off saying we're using rat neurons. Well, we also use human neurons, partly because any results that we get, we would like to be representative of things that can happen in the human brain pretty quickly. One of the surgeons, Tipu Aziz, that we work with, really, if you're talking about rat brains, he doesn't, it's worthless from a medical point of view. For him, it either has to be monkeys or humans, and we're using here human brain cells as well. And the other thing to say is that I described culturing them, growing them in 2 dimensions. Well, we're also now culturing in 3 dimensions. A lattice structure to keep the brain cells alive. The negative is you don't know what's going on in the middle of the brain, but the positive is you can use things like about 30 million brain cells. So 30 million human brain cells in a robot body is where we're at now, to give you some idea. Okay, there we go. So a different type of cyborg where we've got a robot body and we put a biological brain into it and grow it and let the brain develop and so on. And hopefully it doesn't take too much of imagination from your part to say, okay, yeah.
Are you using negative, positive feedback to educate these machines? Do you know how to do that on what brain?
Well, the final answer is we don't really know how to do it. So the answer is what we can look at is Hebbian learning, habitual learning, simply from the process of the brain being in the body, doing this particular task repetitively. So what Hebb had said, if this neuron fires, causes another neuron to fire, every time that happens, it strengthens the pathway that is created. So when you get a stimulating pulse, it goes through a particular pathway and which causes the robot to turn right. And every time that happens, it strengthens, physically the connections grow to some extent. So that is the type of learning we are able to look at and investigate, is habitual learning. It's the same sort of learning if people smoke cigarettes and, you know, it is physical pathways in the brain that cause people to do things, habits. So we're able to look at that. We can apply chemicals to the brain to look at a type of reinforcement learning. So we can say, okay, we feel that when it does this task, this region of the brain is being stimulated. So we will apply chemicals to that region of the brain to enhance growth. So we can, if you like, it's reinforcement in a chemical way. Or if it's doing something that we don't want, you know, let's say it's turning left and we don't want it to turn left, then we can apply chemicals to the part of the brain that we think is causing it to turn left, which will stop it doing that. Or we can, if you see what I mean. So we can do reinforcement in a chemical way, but electrically at the moment we have no idea where the pleasure and pain zones of the brain are, if it has pleasure and pain zones. A lot of the work, people like John Chapin have done work with rats to get rats to go around a maze. I mean, he's one example of the work there. And he describes it as applying stimulus cues, which is reinforcement learning in this sense, that if it does something right, it gives the rat a pleasure signal. A lot of work's been done on that with people like Olds in the past of getting rats and monkeys to press buttons and bells and things like that. But we don't know where the pleasure zones and pain zones are, if they are. I mean, maybe there are some, and if we can find those, then we can start applying more reinforcement learning. So hopefully that answers the question. So it is relatively very early days in research worldwide in this area, but I mean it's very, very exciting because maybe there are pleasure zones there, and so whoever describes them and finds them, it will have moved the thing forward considerably. Then all we got to do is find the pleasure zones with students, and we can start applying electrodes, and we can move education forward enormously. I've got one further section I'm going to talk about, and then we're going for a musical interlude, and then I will get into enhancement. Now this, again, I don't know whether it's science, it's debatable, but it is technology that is used to help therapeutically. Deep brain stimulation, if anybody has a relative with Parkinson's disease, they may have already received implants. It does involve electrodes positioned in the central area of the brain. There are three regions: the globus pallidus, the thalamus, but the most successful one appears to be the subthalamic nucleus. And this, essentially what happens for deep brain surgery, deep brain stimulation, is the surgeon will drill a hole down into, so very high accuracy is required, down into the central region of the brain, and then will send this shaft which has either 4 or 6 electrodes on the end of it. The number of electrodes is to assist the surgeon in getting exact positioning of where currents are applied. Typically, for somebody who has a right and left Parkinson's, they would then need 2 sets of electrodes for deep brain, both sides. But some cases, just one side. It's used mainly for Parkinson's disease, but it's also used for, in some cases, for people with epilepsy, for Tourette's syndrome, and for clinical depression is an increasing range. People are really suffering from depression. Now I'm going to show you how it works, how it can work, I should say, and then I'll quickly describe what we're doing as far as the research is concerned, and then we've got a musical interlude. So what you're going to see is a man who has Parkinson's disease, so you'll see what it's like with Parkinson's disease. He has received the deep brain electrodes, and you'll see the assistant switch on the power packs. Now, one thing to say here, those of you that are into evolution of humans and so on, probably wondered why we have quite a bit of space here in our bodies. There's not really a lot of organs, there's not really much stuff here in our bodies. Well, the reason is, it's really one of those predictions for evolution, is that it is very good for putting pieces of technology. And power packs and all sorts of things get put here because there's just so much space there. It's not, you don't have to take things out. And the power pack for this stimulator is positioned here, and then there are wires running underneath, or subderm, underneath the skin, into the electrodes. So you'll see how this person is. First of all, with Parkinson's disease, then the assistants will switch on the power packs and you'll see how he is with purely electronic stimulation of the brain. This is a genuine guy who has Parkinson's disease. What you're going to see is relatively typical. This is how it can operate.
In 2 minutes, what was the status of Mr. Plessman when he was referred to us by his neurologist in Belgium. And you see him before surgery without drug, unable to stand up by himself. He's helped by Patricia Limousin, who is a neurologist in our group, and he's not able to do anything of, as he will tell you, makes your life looking like normal. He's not able to walk. He has having dystonia, which are muscular contraction, deforming the different joints, and this is the best he could do without the drugs, with the help of people around him and mainly his wife and friends. He was referred because the drugs were not working anymore. He was not having any more improvement, and as he will tell you, he was just stuck to a wheelchair. This is after surgery. You see the tremor. We turn one of the 2 stimulators which were implanted with electrode into his subthalamic nucleus, which is a tiny part of the brain, and you see that in a few seconds the stimulation induces a stop of the tremor. This is still visible on the other side. We will turn on the stimulator on the right side, and you will see something even more spectacular than that. You will see that the patient feels again free, and he resets himself in his chair in the position where he feels the most comfortable. He will obey Dr. Pollack in doing some tests, even if he feels that those tests are a little bit useless as compared to the feeling he has. He can do that almost normally. On the right side, should I do it longer? Does he say? And he will show it on the other side. And then he will walk. He stood up alone. He's without any drug. You see him walking, turning. It was a few days before the Vienna meeting on movement disorder.
Personally, I don't care if you define that as science or technology or otherwise. I'm not bothered. If you can do things like that and help people in that way, then for me it's important that you do it, I have to say, is my standpoint. So the definition is not critical. as far as I'm concerned. What we're doing now is working with surgeons in the John Radcliffe Hospital, Oxford, using the electrodes that are in the brains of people with Parkinson's disease to record the signals, to monitor the signals in their brains, the electrical activity, and to link them up with the tremors and the muscle locking, the dystonia that occurs. Partly it is to try and see if we can provide stimulation on demand. At the moment the technology stimulates all the time, so there's worries about long-term effects and so on. But it uses up the power packs, which have to be replaced every 2 years, which is not such a good thing. So we're trying to get the power packs to last a lot longer, so the electrodes only stimulate when they need to stimulate. But in doing so, the system needs to predict when tremors are going to occur before they occur, so that then you can stimulate so they don't actually occur, if you see what I mean. So we're monitoring in real time electrical activity in the brain and using artificial intelligence computer systems to understand or to try and understand what's going on in the brain and to link it to the tremors and so on. So that work is ongoing, that research is ongoing now, so that the future stimulators will just stimulate when they need to and not all the time. What it is doing though, and again, I don't know whether you want to call it science or otherwise, what it is doing though is giving us more of an indication on Parkinson's disease itself. And what we're finding with the surgeons is, rather than there being this Parkinson's disease, there are actually subgroups in different people that the electrical signals in the brain seem to be of a different nature, which we're trying to understand more of at the moment. And it may well be that once we chop it up, so there's this group of what are now called Parkinson patients, and this group, so that treatments will be different for different people. So it's also helping us, using artificial intelligence to understand a bit more of what's going on in the brain will help in the longer term. I'm going to get on to enhancement in a minute, which raises all sorts of questions. At the moment, we've looked more at therapy, and when we get into enhancement, really it's saying the possibilities are there. We don't have to put up with how we are as humans. We can use technology to improve our abilities in all sorts of ways, particularly mentally. And clearly that raises questions between well, some people may not want to be enhanced, and they may not like other people being enhanced. And then there's others who do, such as myself, who do want to be enhanced and have all sorts of extra abilities. And therefore there's this bit of a dilemma in the future. Why should we stop people who want to be enhanced and have other abilities? And I think now, that is a cue. I'm trying to give a cue to the musicians are never here when you want them, are they? Come on, musicians. So I think there is, what I understand they're going to do is to give an indication of this conflict. Thank you very much for that. Enhancement. For those of you that have felt you're okay being a human and there's nothing more to it, well, there's sort of possibilities, certainly as you get older, having an improved memory. This is taking some of the advantages of technology, artificial intelligence, we know AI, fantastic memory, brilliant communication, sensory input we've looked at before. So these are potentially ways that you as a human could upgrade, enhance a little bit. Memory, there's something there to remind you of this, that and the other. Communication is the big one, as we'll see. I mean, to be honest, how we communicate as humans is absolutely pathetic in comparison with technology. And the possibility of upgrading our means of communication is tremendous. I mean, when you think of it now, all of us have highly complex signals, thoughts, images, feelings, emotions in our brains. That's what's going on. And if we want to communicate those to another human, what we do is to convert those electrochemical signals, complex electrochemical signals, into trivial coded mechanical signals, either pressure waves via speech or by mechanical movements. And then they go along, converted back into electrical signals enormous distances, and they're converted back maybe through sound, and our ears were again pressure waves, mechanical signals. So the possibility of getting over this interface problem of sending signals directly from brain to brain is clearly something, that's where we've got to move to, irrespective of anything else. This is Campbell Aird, and he lost his arm due to cancer. He's been given this robot arm, but you see what he's doing, you see him flicking the switch here to operate the arm, to move the elbow and the hand and so on. And really, which is a bit crazy, I mean, what we really want him to do is to operate the hand directly from his brain and to feel what the hand's feeling in his brain. But what this needs is an interface between his brain, his nervous system, and the wires, and back the other way, so we can send signals bidirectionally. But let us assume for the moment that we have a bidirectional interface. So signals from his brain can appear on the wires and move the arm. So we can give somebody, as long as mechanically it's all right, we can give them an artificial arm or a leg. But that is looking in a limited way. What we're talking at there is putting brain signals, not just on the nervous system, neural signals, but on wires. And if we put signals on wires, well, we can plug into them and send those signals where we want. We can send brain signals across the internet if we want. They don't have to be restricted to bodies. So what it's saying is if we have a bidirectional interface, I'm sure it can help somebody who needs an artificial leg or arm, but it means for all of us, your brain and your body don't have to be in the same place. Evolution has made that happen, but with the technology, that isn't how it has to be in the future. As long as you can plug your nervous system into the internet, you can have bits of your body wherever you want them, different continents, planets, or whatever. That's what it holds for us. So what have I done in that respect? Well, this is me on the operating table at the Radcliffe Hospital in Oxford. 4 neurosurgeons were involved, and what they did was, this is now called the brain gate, and this was surgically implanted in the nerves of my left arm. Now I have to say, it wasn't for medical purposes, I didn't have a problem that this is for. This was for research. I would like to think of it as scientific medical research. But we were looking to link my nervous system with a computer to assess technology to help people with disabilities, but also to look at the potential for enhancement.
One man in tune with technology is the world's first cyborg. Part man, part machine. Kevin Warwick, cybernetics professor at Reading University, England, took a leap into the future as long ago as 2002. For 3 months, a silicon chip was implanted into the nerves in his arm.
At that time, no human had had an implant of this type before.
It was a procedure that until then had only been tested on chickens.
Would the body reject it? Would it affect the way I moved or my sensory capabilities? I could have lost the use of my hand. Could it affect my brain? Ultimately, could have sent me crazy.
Kevin was plugged into a computer which monitored the nerve signals from his brain to his arm, receiving and transmitting them as radio waves. With the signals from his brain, Kevin could not only turn on lights, he could control a wheelchair. And from 5,000 kilometres away via the internet, he succeeded in getting a robot hand to mimic his own hand movements. His most impressive experiment involved his wife, Irena, also having a chip implanted in her arm.
The communication experiment between myself and Irena was vitally important to me. This was the highlight of the whole experiment.
Kevin wanted to discover if it was possible for his brain to receive and feel signals from Irena's brain.
When Irena first moved her hand, it actually felt like a charge running up my index finger. It was a phenomenal feeling. Literally, every time she moved, my brain received a signal. There we were communicating for the first time in the world, nervous system to nervous system.
It was the first time two people had electronically communicated by thought alone.
In the short term, we're going to see implants used to help people who are paralysed switch on lights, operate the TV, just by thinking about it.
In 30 years, he believes we'll all have chips in our brains.
But ultimately, having extra memory, having downloads from the computer, uploading from the brain. Earth is going to be controlled by cyborgs. Humans are going to be something of a subspecies.
We'll be half man, half machine, with super memory, super senses and superpowers.
I think quite clearly that's where we're going. Superhuman. And there's the jewel. So a little bit of Nietzschean philosophy thrown in. Oops, where's that gone? There's human error in pressing the wrong button. And now I've got to try and find... can anybody see the arrow?
Excuse me, while you're filling with that.
Yeah, sure.
I've been thinking for many years about the experiment you applied. I'd like to know how did you feel? What pulse did it give you first? We looked for about 6 weeks at purely monitoring signals, so neural signals, and then use them to control a robot hand and switch on lights. So we just picked up signals and got technology to operate, and we're learning a bit about the signals as well. I then started to learn to recognize, so we hadn't done any stimulation by that time. I then started to try and learn to recognize the pulses. And we were putting biphasic pulses of current, positive, negative, into my nervous system. We didn't know what magnitude my brain would understand. We didn't really know what frequencies, what shapes and so on. So we had to try different things. It took about 2 weeks of trying different things before I could actually recognize pulses. And what sense my brain made of them, to start with, was every time a pulse came in, it was more like a charge running down my finger. That's the sense my brain made of it. So we put a current pulse into my nervous system at that point, and I was wearing a blindfold, so I couldn't see what was going on. I mean, essentially what they were doing was like a blind trial. All I would hear was a click. Maybe there was a pulse applied, maybe not, I didn't know. And I was trying to, what my brain started to recognize faintly was a charge running down my finger. Now the next 4 weeks we were doing that. It was a boring 4 weeks. We were doing, every day we were doing that. And my recognition rate improved from about 70% accuracy to 100% accuracy. So my brain tuned in on the pulses. It still recognized them then. If there was a click, it's a charge running up my finger. But when we then did other experiments,
like with the robot hand, we had feedback from the fingertips in the robot hand. And with a blindfold on, because I knew we were doing the robot hand experiment, my brain understood it as a signal, fingertip signal, that gave an indication of force, pressure. It didn't think of it in any way as being a charge running down my finger. So it depended very much on what we were doing, and my brain was happy, oh, that's what we're doing, this is what the signal means. So we had opened up a pathway into my nervous system that my brain was then quite happy, that's what we're doing, that's what the signal means. I think which is great, from our point of view, it's a positive thing, but it means that your brain could easily be fooled into thinking this is what it is, when in fact it was something else. But we know that visually, you know, you're looking at straight lines or the gorilla playing basketball, we can easily get fooled into thinking one thing when something else is actually going on, which is a negative of the human brain, and filmmakers use it all the time. But we could use it, I would like to think, scientifically, to try different things. And so what it felt like, when my wife sent me signals, what it felt like was, that's my wife sending me signals. It didn't feel like, oh, that is painful, or that is hot, or that is a charge. It was a signal that my brain was picking up, that it was quite happy, that's ding, 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 that's what it means. Just like now, you're looking at me, your brain is receiving all sorts of electrochemical pulses from your eyes. It's quite happy. Well, maybe it's happy or not, I don't know. But it's taking the signals, it's understanding the signals for what they are, for what it's learned to recognize them as. It's not like, oh, this is painful or anything like that. And it's not. It's happy to recognize them for what they are in this sense, a visual signal, and audio is the same. And this is the same. So I feel we can extend our sensory input, and our brains will adapt. And various people I've spoken to with cochlear implants, where they've had quite poor hearing and they've received a cochlear implant, particularly the high frequencies. Maybe they've never in their life heard high frequency signals before. And when they hear them, first of all, it sounds tinny. They describe it as an electrical pulse. They even describe it as that way. Their brain doesn't know what to do with it. And then they start to link it to, they'll see a little bird going like that. And then they can start to sound, that's what it is, it's that. And they don't describe it as electrical tinny anymore, it's bird song, they now know, or whatever the high frequency signal is. So our brains are actually very good at adapting and moving into new signals that we haven't associated with before, and hopefully that answers the question as fully as I can. But it wasn't painful, but it is unfortunately a very personal experience. So try it and see. And now I know, but very good question. I did try. I'm going to very quickly run through this, and then how long are we going to have for questions? Am I supposed to stop now, or
the rest of our lives?
Are we?
So, we should start the next session 1:30.
Okay. Well, I will run through this very quickly, and then I want to do at least one Turing test thing, so I promised you that. Ultrasonics, we did try the same, like giving an indication of distance. My wife, her jewellery changed colour. This was from the Royal College of Art in London. A student put the jewellery, changes colour from red to blue. We linked it to my nervous system. Best way of operating it. If I was calm and relaxed, her jewellery was blue. If I got excited, the jewellery started flashing red. I think you can imagine all sorts of things, and I will leave you to. This was Columbia University, New York, where we put my nervous system real time onto the internet and linked up to the robot hand, as I described in England. So I moved my hand in New York, neural signals across the internet to move the robot hand, fingertip sensors back to stimulate my nervous system, which I could understand how much force the hand was applying. And then the communication experiment between myself and my wife. She had 2 electrodes pushed into her nervous system, not the nicest experience for her.
but it did operate as we were describing. When she closed her hand, my brain received a pulse. So we electrically linked our nervous systems together, and using neural signals that we could associate with movement, but using neural signals. So there was a direct electrical route from a brain down the nervous system, across the wires into the computer, back into the nervous system and up to the brain.
Were you able to override one another's hand voice?
When I just recognized it as a pulse. So it wasn't, I could have held her hand and so on, but if she moved her hand, my brain received a pulse. It was as simple as that. It wasn't when she moved her hand, my hand started moving or anything like that. It wasn't that. It was just my brain received a pulse. So I think we would have needed quite a complex, it's much more difficult to do that, to get to control externally one person's hand moving. You can do it via muscles easily, but to send pulses, because the brain starts acting against you and so on and so forth. I'll pick up more questions because I want to. The one final thing, which is a little bit different, but I promised you it, so I'm going to give you. This is what it is Turing's imitation game, and it is machines in conversation pretending to be human, and essentially you as an interrogator have a split computer screen. Behind half of it is a machine and behind the other half is a human, but you don't know which is which, and you have to converse with both and find out. After 5 minutes, Alan Turing said 5 minutes, so it's not a long time, which is the human and which is the machine. And this is taken from last year at Bletchley Park, which is where Alan Turing did a lot of his work on the Enigma code. It was 100 years after Turing's birth, and I'm going to give you a couple of transcripts, so hopefully. I'll read it through. So you don't know, the judge is human, the entity, you have to decide, is it machine or is it human, is the point. So judge, here we go. How do you feel about this encounter? Entity, I can only comment once we've had sufficient of it. Judge, fair enough. Anyway, this is exactly how it came. This is not spelling mistakes. This is how they were. I almost didn't get here today. Entity, why is that? I felt very dizzy when I woke up and it was hard to shake off. And you had to make it on time anyways. Good job. Thanks. By the way, I meant dizzy. Bad typing. I had to drive faster than normal. Entity, and you didn't get any speed limit fine. No, luckily there was an interesting thing on the Today programme this morning. Today programme is a Radio 4 programme in England. Entity, and what is it, this encounter? You mean the thing on the programme or the chat we're having? Okay, so the question is for all of you now, is the entity a machine or is it a human? Simple thing. So have a think. Now, the way this test works is if you don't answer, it works in the favour of the machine, because the way Turing describes it is about making the right identification. So if you don't make the right identification, the machine wins anyway. The machine is trying to pretend to be human. This might be a human, it might be a machine. But I want you, so have a go. Please don't sit here, I'm not going to take part. You have to have a go and say either human or machine. We'll see. Who thinks this entity is human? So 7 or 8, 9. Who thinks this entity is a machine? Hopefully, we don't need too much statistics. The vast majority said machine. So the judge here was actually a professor of artificial intelligence, and the decision by the judge agreed with you, everybody, that the entity was a machine. The entity was a male human and a non-UK student, in fact. So sorry about that. Can we do one more?
I know we're running out of time, but here we go. So these are actual transcripts, and the letters and the words are exactly how they appeared, so if there's spelling mistakes, that's how they appeared. And it is 5 minutes, which is what Turing said. Here's another one. Hey, so this is a different entity from before. Hey, just to lighten the mood a little, what's brown and sticky? No idea. What's the answer? A stick. So, anyway, what's your name? Sheldon Cooper. What's yours? As in the guy off the Big Bang Theory. Should explain, Sheldon Cooper is a character in a comedy program called The Big Bang Theory. As in the guy off the Big Bang Theory, I don't believe in the Big Bang. So are you religious then? Aren't we all? Well, I like to consider myself as an agnostic. Which religion is it you follow then, if you don't mind me asking? You can ask what you like, it's a free world, who am I to mind? Okie doke, here we go again. Now, so we do, human, machine, the same. Who thinks this entity is a human? Oh, fewer than last time, so it's probably 5 or 6, maybe, if we're looking. Who thinks this entity is a machine? So, no question. Still few people with you. Remember, the machine wins when you do that. So here we go. The answer to that one. The judge decided they were definitely conversing with a machine. There we go. I enjoyed being a hidden human. I have to say, the one thing in my defense there, one thing you're asked to do is not say who you are, not to give your action, because that would give the game away. So the Sheldon Cooper thing, and machines, you know, they lie. All sorts of questions as to lying and what effect it has. I was just being me. When my wife saw the transcript at the end, she said, well, that's typical for you. You know, you're an awkward sod, and that's how you like. So very typical responses there. One issue was, though, in this, I was acting as a hidden human 6 occasions, 6 different times. And I got classified as a machine 5 times. And the one time it was an unsure, the person didn't know. So it was not classified as a human. I'm going to give you one more, and then we'll wrap it up.
So, I can now understand much better why you don't get the rejection from your body.
You've got it. I'll do one. Yes. Okay. I'm happy to wrap it up. Yeah.
So Asko here has a microphone, so who has any questions?
Well, I think that was not Turing test, because originally the Turing test was that the user should guess was it real or not. So that was pseudo Turing test only.
I'm not sure that I understood the question or whatever it was. Can anybody say what the question was? I understood you saying it was not my interest, or... Sorry, I was trying to answer it if I could.
When Turing presented his test, the purpose was that there were not outsiders who should claim was it real or not.
This is in the Turing test.
It's not.
Okay.
It's not what Turing means to be a Turing test.
Okay. What we just, I will answer it, yeah. We followed exactly the lines that Alan Turing described. He described it, what he called it initially was is an imitation game, but it's become commonly known as the Turing test. He stipulated exactly that it should be done as a 5-minute test. He stated that in several papers. He gave different versions of it. The original one was a man and a woman, and the woman disappears and you have to decide which one's which. My own reading of that is that this is 1950. He put the this test originally. And computers, there weren't computers at that time, so the man and the woman he was using as a sort of a parable to try and get people, all right, this is a computer. Now, although we can't speak to Alan Turing because he's been dead for many years, what I have been able to is to speak to several people who worked with him, his colleagues, both at Bletchley Park, and who were part of what was called the Ratio Club, which was a club of quite clever scientists at the time. Fortunately, my PhD supervisor, who is still alive, was a member of the club and knew Alan Turing very well. So trying to get exactly what's going on in the test, tried to do the best that we can in understanding what Turing was about, and certainly staging the test with machines and humans. That's what we tried to do, but I've tried to give you some indication, as much as anything. Some of the machines are getting quite good at it, and it can be quite difficult to decide. So if I tried to put anything over today with actual transcripts from 5-minute tests, that's what I tried to do there.
Thank you very much for the presentation. I think one of the troubling points of talking about the division between human and machine disappearing is we talk about enhancement, that we are somehow making humans better, and I guess that could be seen quite problematic, especially when we talk about communication, that our communication is so rudimentary. But actually, like, for humans, the way we communicate is one part that makes us human, and like that's part of our culture and how we have different gestures and how we have ways to go around things and so forth. And I think what they said, I'm not sure if that's what you're saying, but in this like funny little video that they had made, the media, that that in the future humans will be like a not the dominant species on the planet, so there will be more robots. Or so do you see any problem with this talking about enhancement, or is it just making us something else than humans?
Well, maybe it's both, or maybe, yes, there are probably problems, but technology has pushed us forward. We are as we are now, and even humans, there's incredible differences between humans. But technology has given us the opportunity to change in different ways, and it depends to an extent on society and culture and commercial interests and all sorts of things as to how we take on board technology. I think it would have been very difficult 30, 40 years ago to accurately predict the effect of networking, and particularly the social effect of networking, which has been dramatic, incredible effects that we even see now. And so here, what I can do as a scientist is to say, look, here we are as humans, as anyone else can do, and this is what technology has to offer. There are possibilities here. If we link more closely, get over the interface problem with technology, then potentially we can do this and potentially we can do that. Whether it will be picked up, everybody suddenly wants to communicate brain to brain. No, it depends on commercial interest, how well it works, what people are prepared to accept ethically and socially at this time. But at least we can look. From my own perspective in terms of communication, I do see it as an enhancement if we could communicate brain to brain in terms of sending all sorts of different signals. I do see the way we communicate at the moment as an incredible bottleneck, that the pressure waves for speech bear little relationship to the thoughts you have, and even if you've been married for 40 or 50 years, you still, why can't she understand what I'm talking about here? I think everybody gets that, and certainly as in the university world, putting ideas across is a major problem. If we could do that in a better way, I think it would help. There's a lot of misunderstandings in the world because of different culture, because of different languages and so on, that if we could try and communicate in a better way, communication is important. So just that one thing alone, I think I would see it certainly as an enhancement. It's certainly different.
But it's you know, what is an enhancement to one person is not necessarily an enhancement to another. But it's there, putting it on the table as a possible way ahead.
Thank you for your lecture. It was very interesting to listen. And you now, as you answered the last question, perhaps you came into what I wanted to hear a bit more about, because you are talking very much about the possibilities. And the enhancements like equal duel between picking up or not picking up. But we all know that it's not as easy in quotation marks, as in a close relationships to do these things. We live in a world with quite horrifying global inequality structures. And we have a lot of earlier examples, of course, beginning with fantasies of Mary Shelley down to Huxley or other persons, but also, of course, in real life with Einstein. What would he have thought if he had known what happened and all this? So I would like you to say some more about the dangers and all these unforeseen consequences that every new technology always gets you into. You have touched upon it, but some more, please.
It is, I mean, my job is as a scientist. So what I'm about is to try and investigate and research and look at the possibilities and report, I guess, as I see them. What then happens, I think for any research scientist, it could be good, it could be bad, and you just live with that. That's part of, if you don't do anything that could be picked up like that, then you're not really a scientist. You're not really doing anything that's going to change the world or shape the world. But what you do could be picked up. You mentioned Einstein. Yeah, I mean, he was more of a theoretical physicist in that, but the theoretical results he came up with did change the world and had knock-on effects. There are different reports on how he responded. I think there is the more pink glasses view that if he had known what he found out later, he wouldn't have done it. I don't know that I've actually seen that quoted, and I mean, he didn't give his Nobel Prize back, so I do wonder whether that is actually true. He might have said it at some time, but I don't know whether he actually felt it. As a scientist, you know, it could be picked up, hopefully for good, some of it, but also hopefully for bad. You hope that it will be more for good. But here, like thought communication, potentially that has an enormous commercial pickup. And if in the UK suddenly a load of companies form and they make loads of money out of it, then I could see that as a positive. Suddenly there's a lot of people that are a lot better off because of that. But other people elsewhere who don't have the technology or could be left behind more because they don't have the technology, so you could see it as a potential negative. And yes, the potential here, whether it is Mary Shelley's Frankenstein that is being created or whatever, but the potential there is for something like the Terminator scenario. But one lives with that is a potential end result down the line. But I think any scientist, it's something you live with. Everything I do, I've had ethical, where needed, I've had ethical approval. So society is putting a guiding steer to the experimentation that I'm carrying out. So I'm happy that society, whether it be hospital authorities or the university authorities or whatever, have looked at what I'm doing and say, that's okay for you to do that. So it's not just me going it alone despite what the outside world. But I think 100 years or so ago, scientists didn't have the same ethical steers. If you look at the work of Pavlov, for example, I mean, he won the Nobel Prize, but it's quite horrifying what he was doing to different animals, but without, as far as I'm aware, approval. So I think now we are much better regulated and you need appropriate ethical approval. So there are checks and balances.
Unfortunately, the bell tolls. The last question.
Hi, thank you for a very interesting talk. I'd like to ask you about one of your experiments, the one with the small robots and the brains. Have you ever noticed any difference in the learning of these brains depending on species, or the species of human versus rat neurons?
This is not going to be good news, I'm afraid. Unfortunately, rats tend to learn much more quickly. I mean, it's part of the species. If you're born a rat, you will, and you're going to go to rat university, you have to do it within about 1 month. All the learning only in a rat's brain, there's still adaptability, and it occurs in the first 21 to 28 days. Then the rat's brain is fairly constant. Whereas with humans, of course, you could probably say the equivalent is 18 or 20 years. And then, okay, still not fixed then, you can still learn, but it's pretty well. So for our experiments, the rat neurons are much better, because within a couple of months period, we can play around with the learning and apply chemicals and do all the sort of things we were talking of in the discussion. Whereas with human neurons, they're a lot slower in the way they perform, but that's inherent in the human life expectancy and style and so on. But at the moment, it is, with human neurons, it is very early days, I have to say. Rat neurons are also a lot tougher. Human neurons are very delicate. If you don't get the right temperature, they die very quickly. Rat neurons can take quite a variety. We've had, by mistake, more that the temperature was up to over 40 degrees centigrade, and the rat neurons were not performing very well, but they didn't die, whereas the human neurons died off. The best to use are actually tumor neuroblastomas. We've thrown them away, and they still, exist. It's so they're toughest of the lot. But rat neurons are a lot tougher than human. Gives you some idea.
Thank you. Thanks.
So after a little pause of 3 or 4 minutes, we continue to the next session called Robotics. Thank you, Kevin Warwick.
Thank you.